Hello, my name is Alex Useche, and this is my talk Anatomy of a Gopher, Binary Analysis of Go Binaries. Hexes and punks. My name is Alex Useche. Like I mentioned, I go by Hexapunk in the security world. I am a security engineer at Trilobits. I previously worked as an application security penetration tester, where I focus mainly on IoT and mobile penetration tests. Before that, I was a software developer. I am a huge Go aficionado, a Rust fan as well. I like messing with binaries and code, and I am a father and husband. Great. So, what is this talk about? We're going to talk about what makes a Go binary different than a C or C++ binary. Uh, to do that, we're going to identify the techniques for conducting binary analysis of Go binaries, and I'll tell you how I got to be interested or get interested in reversing Go binaries. We'll also identify common concurrency patterns in Go binaries and see how that looks under the hood, how a Go routine looks under the hood, etc. We'll be using Go tools to make analysis of Go binaries more effective. We'll see what that means in just a moment. So the basics. So the Go assembler. The Go assembler, and some of you might know this already, it's based on the input style of the Plan 9 assembler. It works on a semi-abstract instruction set, and we'll see what that means in just a moment. The output might not always be a direct representation of machine code. For instance, a move instruction, which is moving a pointer, for instance, from a register to the stack, might actually be a load instruction. It also introduces a set of pseudo registers, and we'll see what that means in a moment as well, and introduces a set of directives used by the garbage collector. So these are the Go pseudo registers, and depending on how much experience you have looking at the assembly code, you may or may not have seen this before. So first, yeah, this is what you might see when you disassemble a Go binary. You might see a frame pointer, F marked with the letters FP, and this is used to reference arguments and local variables. PC is the program counter. SB is the static base pointer. Now, let's look at the output on the right. So we have disassemble code. This is using the Go obj dump internal tools, and we see a call to runtime.new proc here at the bottom right. And in parentheses, we have SB, that's the static base pointer. All that's saying is that the runtime.newproc function is the function name runtime.newproc as an address in memory, and that address is relative to the static base pointer. If you have worked with MEPS binaries, you may be familiar with GP register, and that's very similar. So let's continue. There's also the SP pointer, SP register. That's a stack pointer that just simply points to the top of the stack. It's the same thing as your RSP. If you have worked with x64 binaries, just points to the top of the stack. BP is the base pointer, which in x64, typical x64 C and C++ binaries is just going to be your base pointer, and x0, it's typically a full 16-byte register. So tooling. Now, we're gonna start diving deeper into Go binaries and what tools do you want to use or should you use when working with Go binaries. So obviously pick your favorite reverse engineering tool. I'm a big fan of Radari 2 or Binary Ninja as well. You can use Ghidra, which is free. There are also a myriad of interesting and fun tools to play around if you're interested in reverse engineering. Obviously, you may have heard of IDA Pro, which is a little bit expensive. Again, I'm a big fan of Radari 2 and open source tools for this. You want to complement your reverse engineering work with the Go internal toolchain. And the main tool that I have in mind right now is a Go tool obj dump, and that's because it's going to allow you to print to compile your Go binaries, and it's going to allow you to print this assembly code using the and you will see a slightly different output than what you will see using tools like Radari 2. We'll see what that means in a moment. When you're using Go tool obj dump, you use the uppercase S flag to print Go code, meaning line numbers corresponding to assembly instructions. You will use the lowercase s flag to specify a function, so you can specify a specific function that you are interested in disassembling. This is very helpful for grouping a set of statements and matching that group of the assembly instructions to lines of code from your Go source code. Um, Now, bear in mind that that's going to print instructions left to right. That's what we call that. That's usually that's typical to working with Go tool obj dump. That's similar to AT&T syntax as opposed to Intel syntax, which prints statements or instructions right to left. We'll see what that means in a moment in case you haven't worked with reverse engineering tools before. This is not an option for stripped ELF binaries. Binaries that have been stripped of symbols. The reason why it's because they have been stripped of symbols, so you can typically not use the Go tool obj DOM to disassemble specific functions because we don't have the names of the functions in the binary. However, if you're working with binaries you compile in a Darwin architecture in your Mac computer, then typically this is going to be possible because you typically what happens is the dynamic symbols still remain there, including function names and things like that. So why do you want to rely heavily on the internal Go tool obj dump? This is why. So the output is going to be slightly different. It's going to use some of those pseudo registers that I mentioned. And when I say different, I mean different than what you will see in tools like Rodari2, and we see that here. Um, but you also get a little bit more information, and that's if you, for instance, are using the uppercase S flag, like I mentioned, and you will actually see line numbers. And because you can see line numbers corresponding to assembly instructions, then you can say that, okay, well, all these instructions are matching one particular line in the Go code. And then that makes it a lot easier to not only work with Go binaries and conducting analysis of Go binaries, but also it allows you, if you are interested in learning more about analyzing or reverse engineering binaries at all, it gives you a little bit of help in learning that quickly. And this is the output in Radar 2. So again, the instructions here are left to right, and then the bottom are left to right. So obj dumping Go 1.15 got a lot fancier. Go 1.15 was released at the beginning of August, if I'm not confusing that. And this is what it looks like now. So rather than getting the line numbers, you get actual code statements, the actual line, the actual content of the line. And that can, again, be very helpful if you are trying to understand what's happening under the hood. So for instance, here we have a deferred close function, and then we see a set of assembly instructions that correspond to this particular line of code. So again, that's very helpful. And again, since Go 1.15, the output got a lot fancier. Now you can pass it the flag tag GNU, and that's going to give you the GNU syntax on the right. The syntax is going to be basically AT&T syntax, like I said, but the fact that you get both the native output from Go obj dump and the from the Go tool obj dump and the GNU instructions, the GNU syntax instructions on the right can be very helpful. So you can jump between the output that you get here with the output that you get in a tool like Binary Ninja, for instance. So strings. So one of the things that you want to do when working with Go binaries usually, or when you are working with binaries and trying to figure out what they're doing, is looking for interesting strings in the binary. And you can do that using the strings utility. You can use that, you can just cat the actual binary and grep for interesting strings. And then a smarter way to do that is using tools that are meant for reverse engineering binaries. In this case, I'm using a Radari and I'm trying to look for the string human. So basically, I'm saying, hey, look for all the strings in the text section of the binary and show me the string human and show me where the string human is in that text section. And we don't get anything. Now, if we pass it, we say, hey, look in the entire binary, and this is what IZZ means, and look in the entire binary for the string human, then we get some output. This is different than if you're working with a C or C++ binary, where typically you're going to get the output in the text section. In the case of Go binaries, you want to look for strings in the entire binary. So whatever tool you're using, make sure that you're just looking for strings in the entire binary. This is another tool from Radar called Rabin2, and again, here we're telling it to look for the string human only in the text section of the binary. And here we're looking for the string human in the entire binary, and then we get a little bit of output. Now here's something else interesting that's different from C and C++ binaries. And now here we see a move instruction, and then we see this name here, Abed Nadir. But next to Abed Nadir, we have this other crazy string that it can be difficult to make sense out of. Um, so rather than just having that particular string that's actually being moved to a register, and here it's because it's a move instruction from the for a position in memory to a register, then we see the string plus a bunch of other things that are useless to us at this moment. Why is that? This is because Go does not store non-terminated strings as opposed to C and C++ binaries compiled uh, with Clang, for instance. So this is because all the strings are clumped together in the text section. And Go uses a separate table with string length information. So it says, hey, let's look for this clump for this string, and this string is length 7 bytes. And then it determines what the it's able to figure out what the string is that you stored in your binary. This can make it difficult to find cross-references, and cross-references meaning you're looking for the string human, for instance, in the as we saw in the previous slide, and you're looking to see where that string is being used elsewhere in the binary, so you can see what functions are using that string that might be interesting. For instance, the string password. If you are conducting a reverse engineering of a interesting binary that you're trying to figure out to see if you can find a password in the binary. If you're using Radar 2, you can use tools like this one that I'm linking here that make it a lot easier for you to work with strings and find them in your Go binaries and overcome these difficulties that I mentioned just now. Um, so anytime you're searching for strings, whatever the tool you're using, make sure that you are searching for strings in the entire binary. Otherwise, you might not get any useful output, not just the text section. So that's something that's interesting, and that's different between Go binaries and C and C++ binaries. So functions. So how do you identify functions? So you grab a Go binary, you disassemble it. How do you identify the different functions that are part of that binary? So great. And here is the output that I for Radar 2, where you want to list all the functions. And this is the structure. So you have package.function. It's gonna be the typical the typical syntax that you will see in whatever tool you're using to reverse your binary. So in this case, we have this long package from a tool that I created a long time ago. So github.com/code/gorp. And then usually you will see underscore or dot, and then you have the name of the receiver structure. In this case, it's the debugger structure, and then you will get the actual name of the function. So here we have the gorp debugger package, the debugger structure, the debugger receiver, sorry, and then the start target function. So we know that the start target function is a function with a receiver debugger. So that's typically the structure, the syntax that you will find. And it might be like this one right here with the underscores, or it might be the package.receiverStruct.method, depending on the tool that you are using. But the point here is that it's fairly easy to figure this out if you are familiar with Go, locating functions in non-stripped Go binaries. And this is what it might look like if you are looking at the disassemble code in the in your favorite tool for reverse engineering. So we have different calls to different functions, and again, here's a package. Then we have the structure, the receiver structure, DOM, and then we have the function. So pretty simple. Now, within Go, as you guys know, you can write C Go functions, and they're going to look a little bit different, but they will also be fairly easy to locate. So in this case, this is the typical syntax. You have a sim underscore cgo underscore whatever. It's gonna be here. For instance, I wrote a C function called greet, a cgo function called greet, and we have cgo underscore a ID, then we have cfunc underscore greet. So we have cgo and cfunc as indicators that this is a function that was written using cgo. Typically, this is interesting for security researchers because that tells you that, hey, they are using cgo, so the likelihood that this is vulnerable has increased at this point. Um, in this case, I only wrote this function, the greet function. So that's the only function that I wrote, but within it, I'm using the free cgo function and the malloc cgo function. So even though I didn't write those explicitly, then they should also show up in your output when you're listing functions in a particular binary. So um, that's pretty neat. So conventions. We're gonna start with a prologue. So what a prologue is the beginning of a function in the disassemble code, and this is what happens you typically in C. We push EBP. EBP is the base pointer. So what we're doing is basically saving the base pointer and the stack, and this is the base pointer from the caller function. And the next thing that we're doing is we're moving ESP, and this is again Intel syntax, so it's right to left. So we're moving ESP, the stack pointer, to the base to EBP, the EBP which points you typically to the base of the stack. This is the EBP register. So we're moving ESP to EBP. So simply what we're doing is saying, okay, so the base of the new stack, it's gonna be where the top of the stack from the previous function was. Then we see in this case we see a couple of push instructions where we're pushing more perhaps pointers to the stack, and then we have sub ESP where we're actually setting up the stack by because the stack grows towards lower memories and address, then what we're doing was increasing the size of the stack so that we can start so we have a stack set up for the current function that we are looking at. Now this is going to be a little bit different in Go, or rather significantly different. This is because so Go routines have a small stacks by default, right? So 2048 bytes. If you look at the source code in Go, you will see this value stack min. This is the minimum size that Go routines will have. And what will happen, and here we don't see the push EBP, move ESP to EBP, we don't see that here. What we're instead seeing is this loop where we are, because Go can be sure that a function will outgrow the stack, given that Go routines are not deterministic. For instance, in the case of a recursive function, where we don't know how big the stack might grow, then it has to do to perform a specific set of checks. So what we're doing here is we're growing the stack, we're doubling the size of the stack as needed until we know that the size of the stack is not going to that the function will outgrow the stack, right? So what happens is we do a comparison against a stack guard, and this is the comparison that we're doing here. And if it is not sufficiently big, then we call runtime more stack, which what happens is it grows the size of the stack, and then it's gonna keep doing that in a loop until it knows it's safe, and then it starts running the statements that are that pertain to this particular function. So the stack grows, and pointer on the stack are updated, and we continue execution of the stack. So it's sort of interesting. You will see this in really most functions that you look at. And again, this is because Go routines are non-deterministic, so Go has to make sure that again that a function won't outgrow the stack. So calling conventions. Now the calling conventions are gonna be different in Go binaries than in C and C++ binaries, right? So the return values are placed in the stack, as opposed to C, where return values are typically placed in the registers. So for instance, right here we have the end of a function, and what's happening is we're moving the zero value to a position in the stack, and next we are restoring the stack, and then we are returning. Here the zero value corresponds to false, and it's set in the stack, and then the caller function can locate that return value in the stack, as opposed to the C and C++ binaries where it locates that from it grabs that um, from registers instead. Arguments are also moved to their stack rather than registers, and here we see a call to the check password function, and what's happening is we are moving values from registers to the stack, and then we call the specific function, and then this function can locate those values in the stack rather than registers. So identifying language underlying language constructs, it's key to understanding Go binaries. So you can almost look at a disassembled function from a Go binary and have a pretty good idea of what's happening by looking at the internal Go functions. Usually part of the Go runtime package, for instance. And this is because stripping function names is not easy using the internal Go tool. So if you do, typically the documentation tells you use Go build with LD flags S and W to strip symbols. So, but usually what happens is that you can only strip the dwarf symbols table, but you still have dynamic symbols that point to names of functions. So it helps to become familiar with common functions from these packages: source runtimes, source IO, source net, source OS. This is the key to reversing Go and identifying concurrent code and pointer operations in particular. So for instance, here we have sim runtime.new object that tells us that we are creating a new object and we're placing it in the heap. Here we have a wait group, so pretty simple. We know that we are calling a function and we are placing it in a wait group, and then we have runtime.newproc. This is a function. This indicates that there's a function that we are calling as a Go routine. We'll go a little bit further into that. If you want to identify, for instance, that there is a receiver dereference, you will typically see this call to sim the runtime typed main move. So for instance, this is the disassembled code for this particular function. This small function turns into all these statements here on the right. So what's happening is we are saying, okay, so uh, we are calling runtime.writeBarrier. That indicates that we are asking the Go garbage collector whether the garbage collector is busy to do this assignment. If it is not busy, then the garbage collector does that assignment, and then we call sim.runtime.typeMemMove, so the garbage collector does this the reference the variable s, the receiver, and does that move operation, right? If not, we perform that. The function itself performs that assignment operation, as we see here in the middle of this output on the right. So more Go internals. So investigating low-level functions is key to and getting familiar with what they're actually doing. It's key to understanding what a Go binary is doing when you are reversing the binary, obviously. So again, let's look at type move, where we saw that at the reference, where we're trying to dereference a receiver. And then there are a couple interesting things here that happen is, at least for a security researcher, is that we see that the source is actually passed as an unsafe pointer. And then there's a comment here that it tells us that there's a race. So when we see this type of operation, we know that there's a potential race condition. Um, so basically, because the source can change before that operation completes. And again, this operation is in the source runtime and barrier. This is usually indicative that this is done by the garbage collector. So Go routines, Go identifying Go routines is fairly simple. If we see the documentation for this particular function, sim.runtime.newproc, it just tells us that it creates a new Go routine running function with a specific size of bytes that's passed as an argument. And then we put it on the queue, and it's waiting to the Go routines queue, and it's waiting to run. So then let's see. So we have sim.runtime new proc, and this is for this particular function copy println, and then we're passing it the variable test. The variable test is 4 bytes long, and then we see that here. So we are passing the pointer to the function, and then this is this value that's moved from RAX to the stack, and then we have the size of the variable of the argument, which is 4 bytes. Same here where we see the word gophers, for instance, where we're passing to the function for range a different size argument. It's 7 bytes long. So again, same thing. We are placing the pointer to the function on the stack, and then we are placing the size of the argument to that function on the stack, and then we call new proc. So it's just pretty simple to identify Go routines and disassemble Go code. And then this is how the output looks like. This is that exact same function, but using go to obj dump, where we see that everything is going to be RIP relative. So rather than, and again, these are values that are placed on the stack. But again, the output is going to be a little bit different because it uses those pseudo registers that I mentioned a moment ago. And then like right here where we are actually loading the effective address, that's what LEA usually means, or always means. We're loading the effective address of the particular function, and then we place it in an AX. Eventually that goes on the stack with the size of the arguments to that function, and then we call runtime.newproc. So what to look for? So yeah, if you're looking for concurrency patterns, look for calls to sim.runtime.newObject. Usually that also means that there is a variable that we're allocating on the heap rather than on the stack. Sim.runtime.makeChan, obviously when you are creating a channel. Wait group, when we are adding a function to a wait group. Differ proc stack, differ return. Those are all functions indicating that we are using concurrency patterns in the Go code. Anything that's using cgo will have this particular syntax. Again, cgo underscore malloc, cfunc underscore cstring, etc. Functions corresponding to the garbage collector so they will basically point out that hey, there's garbage collector is doing some work here. It's gc.writeBarrier, gc type move. So basically read the manual. This is the main. If there's a big takeaway from this is that the more you know about Go internals, the easier it will be to disassemble or to understand, reverse engineer Go binaries. So one thing that Go security researchers are really into or like to investigate is Go error handling, because error handling in Go can be super clumsy and manual, and we know that we have to continue to we always have to do that if error doesn't equal nil check. So we're looking for bugs. It is worth taking the time to identify in a Go binary missing error handling logic. Now, an error, as we know, is a Go interface, and an interface under the hood consists of a pointer to a vtable, which contains function pointers that contain to the virtual function, and a value pointer. right? So knowing that, it allows us to one identify this pattern, this super common pattern in Go code, where we are checking whether an error is nil or not. And it also allows us to conversely locate missing error handling logic. If we know that a function that we saw in the binary might return an error, but we don't see that check, then we know that there is a missing error handling logic. And there might be a potential vulnerability, there might just be a potential bug that we might want to explore further. So for when checking for error doesn't equal nil, we load the error vtable and error values. So like right here, we're calling set options, right? And set options returns potential error, so which could be an error interface or it could be nil. So this is what we're doing here. When we return from this call to set module options, then we are doing when we're performing this check, we are checking for one that pointer to the view table, two the value which are both in the stack. We compare those two, and then if it is nil, then we continue the or if it is nil, then we continue the execution of the function. If it is not nil, then we return the error, and we see it here how we are placing the again the pointer to the v table and the value of the error are both placed on the stack before we restore the size of the restore the stack and then return. So that's error handling. So let's say that you want to research a Go, and particular Go binaries. Obviously, write Go, which I know a lot of you watching this are already doing. So that's great. Investigate pragmas. So playing with pragmas can be a lot of fun. But also, if you are writing Go and then you want to disassemble it, in some cases you might see, hey, I wrote a function called foo, and I don't see my function foo in the disassemble code. Why is that? Typically, that's because the compiler or may have optimized out that function. So what you want to do is on the top of your function, about right above your function, write this pragma, which is go not inline, and that's gonna tell the Go compiler to, hey, leave this function alone. I want to keep it as a function. Do not optimize it away. You can use this pragma go no split if you wanna play with wanna see what might happen with a when a function is when a go routine is being called, and you wanna avoid go having to do that um, stack splitting operation that I mentioned a few slides ago. If you wanna monitor the size of the stack when it grows and shrinks, as different Go routines are called, you can actually compile a version of whichever version of Go is current. Just clone the Go source code, then look for this particular function on their source runtime stack Go. There's a variable called stack debug set to 0 by default, set it to 1, and then when you run your Go code, you will actually, you Go binaries, you will actually see the debugging messages indicating when the stack grows and shrinks. So that can be a lot of fun. If you type go bill tag m, that's going to print optimization decisions. If you use code debug equal gtrace, as many of you might know, that allows you to better understand what the to trace operations by the Go garbage collector, and allows you to understand what the Go garbage collector is doing. And uh, another thing I wanted to mention is, try to leverage tools like GoFuzz and GoSec to check for bugs, and then look for bugs in code that you have on hand, and then compile that. Then, if you have identified any bugs using GoFuzz or GoSec, look at that in a disassembly tool, in a disassembler tool, or a reverse engineering tool, and then just learn that way. Hey, that particular bug looks like this in code, and it looks like this in assembly. So to wrap up, combine Go tools with the favorite reverse engineering tool for easy reverse engineering of Go binaries. Finding cross-reference strings can be a bit tedious, like I mentioned, because of that whole way of how Go works with strings, and how strings are not null terminated in Go binaries. Familiarize yourself with Go internals, as is huge, and I believe many of you watching this already doing. So understand how the Go scheduler works, understand how the Go garbage collector works, and if you're interested in looking for bugs um, in Go, a big area for this for all security researchers is race condition bugs, unhandled errors, and we always get a little bit excited when we see CGO functions in Go code because again, the chances that there is a vulnerability in CGO in the binary increase when there's somebody using CGO functions. So if you have any questions, reach out to me via Discord or whichever method we're using, and then I'll be happy to answer them. Hopefully this was interesting to some of you. Hopefully this was of value. I had a great time putting this together. Hope you all have a great day and continue learning.